I'd like to welcome you, everybody, to this lecture, the sixth in our public lecture series, Science Stars of Tomorrow, run by the Australian Academy of Science. My name's Mark Ropak. I'm a fellow of the Academy. I'll be chairing tonight's talk. The purpose of this series, as I'm sure you know, is to hear from emerging scientists, the potential stars of tomorrow, and in many cases the stars of today. To that end, we're very pleased to welcome today Lisa Alexander. I'll introduce her properly in a moment. First, before we begin these proceedings, I'd like to acknowledge and pay our respects to the traditional owners of the land on which we meet, the Ngunnawal people of the Wiradjuri Nation. It's upon their ancestral lands that the Australian Academy of Science is built. And as we share our own knowledge and teaching and learning and research practices, we would also like to pay respect to the knowledge and learning and practices embodied in that culture, which in many ways is also our culture that we inherit. I'd like also to apologise on behalf of Professor Tim Flannery, who would have chaired this evening's proceedings, but he has not been able to be here, so you have me instead. I'd like to thank our sponsor, the Eden Road Wineries, who supplied the wines that you've been sampling outside, and I'm sure you'll appreciate that they've been wonderful wines, so thanks to them. Dr. Lisa Alexander is a senior researcher at the ARC Centre of Excellence for Climate System Science and Climate Change Research in the University of New South Wales. And her research, as you'll know from her topic, focuses on climate extremes in Australia and around the world. And this work has found, as she will explain, changes in the frequency and intensity and duration of extreme weather events, strongly dependent on the amount of greenhouse gases in the atmosphere, and therefore very much a part of the phenomenon of global climate change. And it's a particular privilege to welcome Lisa because she and I and a number of others have been working on the update to the Academy's Climate Change Questions and Answers document, which you will have seen in the foyer as you come in. The issue of climate extremes and weather extremes and how they're changing, as you will know, is one of the most important questions that we face in dealing with climate change. It's also one of the most difficult because the statistics are tricky, as Lisa, I'm sure, will explain to us. It's a subject where it's very easy to fasten on a particular event and have that reinforce your prejudice, whatever that may happen to be. The thing that we have to do as scientists is to step back from particular events and focus on the whole, on the statistical story. So please join me in welcoming Lisa, who is going to speak to us about will Australia continue to be a land of droughts and flooding rains. Thank you very much, Lisa.
Okay, hello everyone. Thanks, Mike. As you probably guessed, I'm not originally from Australia. I actually grew up in Belfast in Northern Ireland, and we don't really have a lot of extreme climatic events there. But as I was growing up, I had a love of mathematics, and as part of that, I went on to think of some applications that I could apply my skills in mathematics to. And in the end, my PhD ended up being specifically focused on extreme events, and I did my PhD at Monash University in Melbourne. So I do have, while growing up, I didn't have much exposure to extreme climatic events. I've been in Australia now for 10 years, and I can assure you, like everyone else, I have experienced quite a few of them. So tonight's talk is really not just about my own work, although I will talk a bit about that, but it's really about the work that's ongoing in Australia by myself and by many other people. But first, I don't like to do all of the work in a talk, so I'm going to throw a question out to the audience, and I want a show of hands as to what you think the answer is. So my question is, if we think of a global average during the sort of second half of the 20th century, for example, climate scientists have the most confidence that there have been increases in the frequency of, and I'm going to give you 4 options. Number 1 is droughts. Number 2 is heat waves. Number 3 is heavy rainfall. And number 4 is hot nights. So, I need a show of hands from the audience. Who thinks it's number 1? Oh, okay, yeah, good. Number 2? Okay, good. Number 3? And number 4. Actually, very good. That's about a sort of an even split between all 4 questions. That's actually, I do sometimes give talks and ask this question, and it surprises me that on the whole, when I ask it, the audience is quite divided on this. In fact, as I'll show, we do have more confidence in some of these than we do in others. But hopefully, at least part of the way through the talk, you will see which ones we have more confidence in. So luckily for me, the Intergovernmental Panel on Climate Change produced a report in 2012 that was published, and it was specifically focused on extreme events and extreme climatic events. It had quite a few authors that covered 62 countries, and it had quite a lot of review comments. So basically, these documents are produced in draft form, and each draft is thrown open to the public and expert public, and they comment on what's written. And you can imagine that the comments vary from, this is very good, well done, to, this is the worst document I've ever read, and what you're saying is completely wrong. So each of these comments has to be dealt with by the authors of this document. And so it's quite an intensive job. So in that document, there was a frequently asked question. And the question was, is the climate becoming more extreme? And I'll show you a sort of a small portion of the answer here. So while there is evidence that increases in greenhouse gases have likely caused changes in some types of extremes, there is no simple answer to the question of whether the climate in general has become more or less extreme. So, unfortunately, that means it's complicated, and for reasons I'll show in a moment. So even the Intergovernmental Panel on Climate Change couldn't give us an answer to this specific question. But if we thought about temperature, for example, and extremes of temperature, how might extremes be affected, particularly if we imagine that the climate is warming on average? Well, if we just think about a climate, and here, the grey line might, indicate a world that was, or a world that might have been, and here the solid line in the middle would be the mean temperature. You can imagine if that mean temperature increases, we get a shift of the distribution of temperatures to the right-hand side. So how that affects extremes in the temperature world is that we, not surprisingly, get on average less cold weather, and on average get more hot weather. But we also start getting into territories that we haven't seen before, and that would be things like more extreme hot weather, and perhaps, certainly in terms of our experience, we might be entering a scenario where we will get temperatures that we haven't previously experienced. So this is a schematic. Does the actual temperature look like this? Well, It doesn't look quite as nice as that, but certainly if you look at global temperatures, and here I'm just showing the daily minimum temperatures, you can see the period 1951 to 1980 is given by this blue curve, and 1981 to 2010 is given by the red curve. And you can see that certainly in this particular scenario, global temperatures have increased in the mean by 0.8 degrees. But if you think about the extremes, well, in actual fact, the extremes have increased, in this case, by 1.1 degree. And here I'm classifying the extreme as the top 10, bottom 10% or top 10%. And you can see that at the other end of the scale, so we have got less cold extremes in this global average, and we've got more hot extremes. And the extremes have actually changed by more than the mean. And actually, if you think about it in terms of percentages, this top end means that, you know, we've got 40% increase in extremely warm nights. But when I first asked you the question about which extreme did you think we had most confidence in, the first one I asked you was about drought and whether you thought we had confidence in changes in drought. Well, the first thing I want to point out is that drought is actually quite a complex variable, and it doesn't just depend on rainfall or temperature, but it also depends on evaporation and transpiration, and it also depends on how your soils are preconditioned before you have a drought. So it's not an easy variable to assess, and in actual fact there are many ways to describe a drought, and of those we have three main ones, and it depends on your application, whether you're a meteorologist or a hydrologist or a farmer or an agriculturist. So the first one is what we define as meteorological drought, and that's just really a lack of rainfall, so a precipitation deficit. The second one is agricultural drought, and that's really about the soils and how moist or how dry they are. And the third one is hydrological drought, and that's really about the water supply and the groundwater and how much we have. So because of this, the past assessments of drought have actually disagreed, sometimes significantly on a global scale. And in fact, these two results were published, one in Nature and one in Nature Climate Change, so in very high-ranking journals. One basically said there was a global increase in droughts, and the other one said we can't find any change in droughts at all. So they were both right, but they assessed droughts in a different way. And that means that really over the past few years, we've really tried to reconcile these differences that we've seen in the analysis of droughts. And there was a paper published this year looking at really, a lot of the differences come about because of the uncertainties that we have in the observational data that goes into these assessments of droughts. So when the Special Report on Extremes assessed droughts, they came to this conclusion. Based on all of the analysis that had happened previously, they said there is median confidence that some regions of the world have experienced more intense and longer droughts, but in some regions, droughts have become less frequent, less intense, or shorter. And for example, in Central North America and Northwestern Australia. So in fact, in Northwest Australia, we've actually seen droughts that have become less frequent, less intense, and shorter. So since the Special Report on Extremes, there's actually been another Intergovernmental Panel on Climate Change report, which was published last year. And in fact, this statement doesn't really say anything about global droughts, but in the IPCC latest assessment, they say on a global scale, we actually have low confidence in what has happened with droughts. So let's turn to heat waves. That was your second answer that you were given. So Like our Prime Minister, I looked up Wikipedia for the definition of a drought, or a heat wave, sorry. And according to that, a heat wave is a prolonged period of excessively hot weather, which may be accompanied by high humidity. So, what are some of the problems with this? Well, a prolonged period, well, how long is that period? Is it 2 days? Is it a week? Or is it a month? Excessively hot. What does that actually mean by excessive? What is the threshold by which you define excessive? And it may or may not be accompanied by high humidity, but how high is high humidity? So the definition of a heat wave is actually quite a difficult thing. But when we do look at different definitions, and here I'm looking at different definitions for a warm spell, and these are trends over the latter half of the 20th century, and different definitions of drought. So you can see they all point to increases, but the magnitude of those increases is different between the different definitions. And also you can see that where we've got grey areas, we really don't have, we have a lack of data in terms of what's actually happened in terms of drought. But on the whole, we have seen an increase in the frequency and duration of heat waves since 1950, but there are still all of these areas where we don't have a lot of information. So on a global scale, the Special Report on Extremes concluded that there is medium confidence that the length or number of warm spells or heat waves has increased. But they also said that our confidence for certain regions is higher than this. And one of those regions, not surprisingly, is Australia. And if you look at things like the frequency, duration, and intensity, and these are just trends for the last about 40 years, the latest report of IPCC said it is likely that heatwave frequency has increased in Australia. Now, heavy rainfall was answer number 3. And in this case, again, I'm showing trends where blues indicate increases and yellows and reds indicate decreases. And basically, on the whole, you can see that for most regions where we have data, there's more blues than reds. But you can also see that for some regions, Australia being one of them, that there are areas where we have decreases in heavy rainfall. But on the whole, we see more regions where we get increases in heavy rainfall than we do regions where we see decreases. But as you can tell again, our observations are sparse for many regions, and particularly Africa and South America. So, for heavy rainfall, the Special Report on Extremes concluded it is likely with high confidence, and in this case likely means by the IPCC definition that it's got about a 2 out of 3 chance of happening, that there have been significant increases in the number of heavy precipitation events in more regions than there have been significant decreases. But they also highlight that, you know, there are these strong regional and sub-regional variations in trends. Okay, so number 4 answer was hot nights. Well, it turns out that basically on a global scale, and pretty much everywhere in the world that we've been able to analyze this index, and this is like the warmest nights of the year, the top 10% of minimum temperatures. No matter how we slice it and dice it and where we look and what data sets we look at, everywhere pretty much, with a very few exceptions, we're seeing significant increases in this index. So, nearly all data sets point to significant increases in the warmest nights of the year. So, not surprisingly, IPCC concluded that it's very likely, so this is a now not 2 out of 3, but a 9 out of 10 chance that there have been overall increases in the number of warm days and nights at the global scale. And that's actually accompanied by, which I haven't shown, but it's accompanied by a decrease in cold days and nights. So, does anyone want to revisit the answer to the questions that we had previously? Who thinks it's droughts? Who thinks it's heat waves? Who thinks it's heavy rainfall? Still somebody there? Okay, good. What about hot nights? Okay, all right. So just to show you, what was that?
Except in Canberra.
Well, actually, I'm going to show you something about that in a minute. So, in terms of IPCC and in terms of what the global community and global climate scientists have thought about the observations on a global scale, low to medium confidence on droughts, medium confidence on heat waves, but likely in some regions. Heavy rainfall, we think it's likely, but again, we're lacking in data in many regions. And hot nights, we actually have high confidence, and it's very likely. So that's really just to show you a sort of an overview of, basically in terms of where the climate science is, I think what is the perception in the public and the media of where we have confidence and where we actually have confidence can be quite different. So that means we've got nothing to worry about. There's low confidence in a lot of things, and well, having some warmer hot nights, that might be quite pleasant, especially in Canberra, I think. So, but low confidence neither implies nor excludes the possibility of changes in extremes. And it really depends on the quality and quantity of the data and the availability of the specific studies that we're looking at. In terms of a changing climate, well, we still might not be feeling the full effects of that. So in terms of observations, there certainly will be times where we'll be confident in some particular variables and not so confident in others. And in Australia, natural variability is very large, as we'll talk about in a minute. And that's likely to affect these assessments that we're making. So paradoxically, if we look to the future, we might actually be able to say more confident things about what's going to happen than what has happened in the past. And again, I'll try and hopefully explain to you why that might be the case. So let's focus on Australia. And as we know, that was the global scale results that I was showing you. But Australia is already a land of droughts and flooding rains, as we know. And it also has affected by a lot of other climatic extremes, and that things like heat waves, bushfires, cyclones, many other climatic extremes that impact its people and its unique environment. There are also many different climatic zones in Australia, and this complicates matters as well. We go from rainforest, monsoonal areas, down to, no dry season, distinctly dry. So we've got desert areas, we've got monsoon-fed areas, we've got rainforest areas. So it actually is quite complex in terms of the climate. And not only that, there are many drivers of the climate in Australia, from the El Nino Southern Oscillation in the Pacific Ocean, the Indian Ocean dipole in the Indian Ocean. We've got changes in the, or we have a subtropical ridge. We have a southern annular mode, which affects where storm tracks hit Australia. And we also have these high pressure systems, which sit over the Tasman as well. So there's lots of different things that affect the climate and the weather. And that makes it quite difficult for us to assess what has happened in the past, because there is a lot of large natural variability in terms of the climate. But some of the things that we do have some confidence in is that, well, Australia's getting hotter. And if you look to the Bureau of Meteorology trends from 1910 to 2013, these are degrees C per year, and you can see that there isn't really a region in Australia which hasn't seen an increase in temperature. Also last year, according to the Bureau, was the hottest year on record. And not only that, but it was the hottest year by quite a long way. But when we look at these averages, they can mask out some of the changes that we see in extreme events. So, haven't frosts increased? Wasn't Canberra really cold last night? I was reading actually in the paper today about some of the regions that have experienced their coldest nights on record for, you know, maybe 20 years in some regions. And in fact, actually, if you look at trends from 1980 to 2011, and you look specifically at May, southeastern Australia has actually seen an increase in frost days over that period. But if you look more generally at frost days over the whole season, and you look at longer periods, actually there's a very strong decline in frost days over the region. So in terms of understanding, I mean, as researchers, this is an intriguing result, and why are we seeing increases in frosts over certain periods in certain regions? Well, it turns out if we focus in, and here I'm just showing Bathurst in New South Wales in May, and the blue line here is the number of frosts. And you can see that sort of over the longer period, you know, 1950 onwards, we do see a general decline in frosts at this station. But if we look from about 1980s onwards, we do start seeing this increase in frosts as well. And actually that's combined with a reduction in clouds at night, and also with a reduction in the number of wet days. So these things are all interacting and making the analysis of the climate and the climate extremes quite complicated. So if it's so complicated, how do we actually know all of this stuff? How do we know what we know? And one way that we know what we know is through assessing climate models. Now, climate models are a tool which give us a physics-based approach based on our understanding of how the climate works. So it's basically a set of mathematical equations that are turned into computer code, and then the computer code runs a climate model. Now, these computer model codes are about 1 million lines long, so they're quite complicated. But basically, they allow us to look at things like the world that was, and whether our understanding of the world that was is based on a physical understanding. They can also allow us to look at a world that might have been, and a world that might have been if we hadn't have emitted greenhouse gases, for example, or anthropogenic aerosols. And they can also help us to look at the world that might be, so the future of the climate. But in saying that, I don't want to say that this is the only tool by which we assess what has happened. And it is imperative that we also have good observations, because in order to evaluate these models, we need to know that our observations are good and valid, so that when we make an assessment with a climate model, that it's actually, we know that our models are doing the right thing. So are they doing the right thing? Do we have confidence in these models? Well, that depends on what we're looking at. And in some cases, I'm just showing you here, these are observations of sea surface temperatures, and these are observations of changes in the hottest day of the year over land, if you compared El Nino events with La Nina events. And actually, when you look into one climate model, which is a sort of earlier generation climate model, you can see that, well, you know, it looks pretty good by eye, but you can see that maybe the El Nino Southern Oscillation is a bit long and thin. We really don't get the warming that you see so well in the Pacific Ocean. And actually, when you look at Australia, well, this model doesn't look so good. In fact, there's some cooling in this model, whereas, you know, in the observations we see warming. But then when we move to the next generation of climate model, well, this looks much more similar to the observations. And in fact, if you look at Australia, just focus in there, well, again, that looks more like the observations. But of course, we need to also say, well, actually, there are regions where this model doesn't do so well. So there are strengths and weaknesses in these models, and that, as researchers, that's what we try to find out. We try to find out which models we can have more confidence in, and particularly, which ones we can use or not use, and for certain applications. In fact, it turns out that if we use many models, we tend to get a better result than if we just use one. In fact, in the world now, there are around about 40 of these climate models that exist on a global scale. And they're developed in different countries by different centres. So a lot of them have been developed very much independently. But if we look at these warm nights in Australia, comparing the observations in the model, well, the multi-model trends actually look pretty good. But if we compare them Australia-wide on a time series basis, so we look at how they vary from year to year. So the black line are the observations, and all of the different coloured lines are each of the simulations from each of the climate models. You can see that, well, the observations do sit very well in the middle of this spread of models. So for some things, we've got good confidence in our models, but for other things, we don't. So because we can now use these models to look at the world that might have been versus the world that actually was, we can actually see whether our observations sit within either of those worlds. So here, in this case, I'm looking at trends in the hottest nights of the year, just over Australia. I'm just looking at one model here, just to give you an idea. And this black line here represents the observations. So this is the world that could have been, which is a world in which we just have natural variations and we don't have human-induced greenhouse gases. And in the other lines here, we have the world that was. And in this case, for this index, the observations don't overlap with this natural climate. And basically, what that's saying is that we can't explain the changes we've seen in Australian temperature extremes unless we include everything. That includes the natural world, and it also includes all of these additional human-induced forcings that we're putting into the climate system. But that's for temperature extremes, and when it comes to rainfall, and particularly extreme rainfall, these changes become much harder to quantify because rainfall is much more variable than temperature. And in fact, when you look at the world that was, or the world that might have been, which is the dotted line here, versus the world that actually was, well, actually, we could have got these observations in a natural world. So that's saying that the chance of getting this in a natural world is smaller than in a world where we include all the greenhouse gases, but it still could have happened. So these are situations where we have to, really try and tease out these signals, but they become much harder the more variable the variable that you're looking at. So a question that we often get asked is, well, can we attribute individual events, and when there's extreme rainfall or temperatures, a lot of people ask, well, is this climate change? And in fact, in my group, we've actually looked at this, and we looked at the flooding of 2010 and 2011 in Southeast Australia. And what we found was that actually we couldn't pick out a human signature in this specific event. But what we could pick out was a signature from La Nina. and as compared to El Nino. So basically, in this particular instance, the natural signal dominated any anthropogenic signal that there might have been. Now, that doesn't mean there's no human signature. It just means that the natural signature is much larger in this individual event. And in fact, if you look at temperatures, and I haven't shown it in my slides here, but work's been done at University of Melbourne, where they've looked at the extreme temperature events that we've had over the last few years. And they do find that those temperature events are about 2.5 times more likely through a human impact on the climate system. So what about the future? So most of what I've shown has been about the past. And in the future, our choices are going to matter. And the reason I say this is because if you look at what might happen with, in this case, I'm showing dry days here. These are heavy rainfall events, and these are heat waves. And in the future, the different coloured lines here represent different scenarios of where we might go with our greenhouse gas emissions in the future. Now, of course, they all overlap here, but you can see that the red one, which is the sort of higher emissions scenario, tends eventually to sort of win out over the other two in terms of being most extreme. And you can see this particularly in the heat wave scenarios. And in fact, you can also see here, this is the difference between the end of this century and the end of last century. And you can see that in general, we see an increase in dry days. We see an increase in extreme rainfall. And we see an increase in heat waves. And in this case, these dots here are quite important, because what that is saying is that the multiple models that we've looked at, actually the majority of them agree on the sign of this trend. So for droughts and flooding rains, actually the models are sort of, some say one thing, some say the other. But if you look at it on average, you do tend to get this scaling of emissions with the extreme. But in terms of heat waves, pretty much all of the models are saying that this is the trajectory that we're going in terms of the future. And not only that, but how much we emit will determine how extreme those heat waves will be. And a lot of people want to look a bit more closely and at sort of higher resolution. I think Canberra's just missed off this map here. This is some modelling that was done over Sydney. And if you go down to sort of very high resolutions in these climate models, they're usually at sort of quite large scales, 100, 200 kilometres or so. But now, at sort of in particular regions, we can go down to maybe 2 kilometres or 5 kilometres. And in this case, this shows us the heat wave frequency under a business as usual scenario. So if we just continue as we're currently going. In this particular model, under this particular scenario, by 2050, we're going to see about 6 to 9 more heat wave days on average in the area around Sydney. So, just to conclude one more time. Australia's climatic extremes are affected by large natural variations in climate, as we've seen. But despite this, there's already a detectable signal of human influence on some of these extremes. Temperature extremes are expected to scale with future increases in greenhouse gases. And what I mean by that is the more greenhouse gases we emit, the more extreme those extremes will be. But we do have less confidence in some other variables and things like droughts and flooding rains. These are areas that the research community is working very hard on to try and deliver to the public some more confident statements that we can make on these particular extremes. But despite this, the evidence does point towards increases in dryness and increases in heavy rainfall in most regions across Australia. And I think, though, that irrespective of the confidence that we have in our science, we have an important role to play in informing public policy on climate change. And we need to make decisions before we have absolute certainty. And our choices matter. Thank you.
Thank you very much, Lisa, for that very clear and scientifically lucid exegesis of where we stand in this question, this difficult question of extreme events. We now have some time for questions, and so I'd like you to wait to ask questions until we have the microphones available. I think we have a couple of microphones that will move around the hall. There's a couple of reasons for that. The first is so that everybody else in the hall can hear, but the second is a personal reason for me. It's so that I can hear. My hearing is not very good, so it really helps me to hear the question. And when you ask the questions, for that reason, please speak up, project, even though you have the microphone. And I'm going to take the chair's prerogative of asking the first question. And Lisa, it is of the events that you've talked about, we have a wide spectrum of both scientific confidence and also a wide spectrum of, let's call it human impact. That is, things like hot nights in some places people may even see as advantageous. Others of the extremes that you mentioned in many places can be severe to catastrophic. Could you just give us some insight into how the scientific community is thinking about the possibilities not only of the events themselves, but of the cascades, the consequences that might follow from those events, and how that relates to our thinking about the impacts of these extreme events?
Okay. Thanks, Mike. It's a really good question because I think over the last 20 years or so since we've been writing the IPCC reports, Working Group 1, which is the physical science basis. Well, first, we didn't actually look at extreme events at all until the 2001 report. So in terms of assessing extremes, from a physical science perspective, we haven't even thought about it until 15 years ago, even less. But there has been a push more recently, rather than this sort of top-down approach, and we think of it from a very scientific point of view, is to think of the bottom-up approach, which is, how will these events actually impact people? And the types of events that we look at, I think, in the future will have to be driven by the impact that they have, rather than just thinking, well, there's a distribution of temperature, let's look at, the 90th percentile. I think we have to think more broadly than that. And the special report on extremes was quite significant in that perspective, or in that respect, because they combined the physical scientists with the impact scientists. And that was to try and come together to develop ideas and the types of extremes that we might want to start looking at in the future. So there is definitely a push to combine the different fields, and that is what I would call IPCC Working Group 1, the science basis, with Working Group 2, which is the impacts and adaptation.
Thank you. Questions, please. Clem first, and then we'll come here, and then right.
Clem Davis from the ANU. Lisa, you mentioned you actually only just touched on it briefly when you talked about frosts, but the seasonality of some of these events. For instance, when people talk about hot nights, they think about summer. Yeah. But then last year we actually had, 7 or 8 basically heat waves that were in winter and in spring as well. So that gives a different perspective to people in terms of temperature as to whether it's a hot day or not. Would you like to comment on the seasonality, please?
Yeah, so in terms of the definition I showed, actually we don't care whether the hot night happens in summer or winter. So it's relative to the time of year. So it's just the top 10%, for a season or for a month or whatever. But you're right that it does make a difference when you're trying to tell people. I showed the frost days in May, the decreases. But if you look at August, for example, well, it's a very mixed picture. And I didn't show it here, but I thought maybe I should have, because we are in August and we have had some frosts recently. So if it's really dependent at that point too on the region and location that you're in as well. So there's definitely, we definitely have, I think, when we try and communicate this stuff, is to possibly be more specific in what we're talking about. But in terms of the hot nights, while people think of that as summer, it doesn't matter whether we look at summer hot nights or winter hot nights, they're all increasing pretty much everywhere on the globe.
Next question.
Thank you. Rainfall comes in for a mention, but in Australia, evaporation is extremely important. Would you care to comment?
Yeah, it certainly is very important, and that's why when I was talking about the droughts, I was saying how it complicates things as well. So when we try and analyse these things historically, evaporation, so we've got reasonably good observations of temperature. We've got quite good observations of rainfall, but we have much fewer observations of evaporation. So I think part of it is that we need to try and, at least historically, get some more good observations in terms of evaporation, but also to really think about the importance of it in terms of our drought assessments, for example. So when we do look to the future, all I showed was the number of dry days, and that doesn't take evaporation into account. And when you do take evaporation into account, you get a bit more of a mixed picture.
I've got two related questions. Mm-hmm. First one is, you know the term.
Sorry.
So you know the term homogenization of data. Would I be right in guessing that your temperature figures would have been homogenized?
Yes, they have been.
Would you apply the same technique to other things like rainfall?
Good question. So in terms of homogenization techniques, they have mostly been applied to temperature, for sure, and that's pretty much everywhere in the world. It varies from country to country as to how rainfall is homogenized. Some countries do, some countries don't. So for example, Canada does. Australia has a high quality network, but it's not homogenized in that sense of the word. And other countries do and don't. So when we're making the assessment, though, all of these things are taken into account as well. Which countries homogenize, which ones don't, which observations we believe more than other observations.
Just up here, thank you. Please raise your hand if you'd like to be in the question queue. We have one more.
There's a graph which has been around in public for some years of the rainfall in Perth, Western Australia, where it very clearly shows a severe step change. I can't remember the details of it, but what's in my head is the step change from a certain high level to a certain low level. Are you familiar with that?
Yes.
Wondering if you'd like to comment.
Yeah, so it is a very famous graph, and in the mid-1970s, Perth experienced a significant step change in rainfall, and actually again in sort of the 1990s. So the graph that you're talking about sort of shows Perth rainfall from the 70s. It drops by quite a lot, and then in the last like 20 years it drops again. So the reasons for that are being studied, but one is that it's actually changes in the synoptic patterns that are bringing rainfall to Perth, and actually the storm tracks appear to be shifting southwards, and that's related to sort of an expansion of things like the Hadley cell, and so with warming we get expanding cells in the tropics, and they tend to move storm tracks further away from their preferred location. So there is certainly some evidence, and there's quite a lot of studies have been done, particularly in southwest Western Australia, that this effect is real and that it has happened, but it's related to these shifting storm tracks. And actually what I didn't show is if you look into the future for rainfall over Australia, pretty much models disagree pretty much everywhere on whether we'll see increases or decreases, except in southwest Western Australia, where they all agree on a decrease. So it's a very, very high confidence in what's going to happen there.
Yeah, that's a particularly interesting one because of the phenomenon that Lisa just said, that is one of the clearest examples that we have, both in the past and in the future. So that's absolutely right. Brian, please.
Brian Walker from SARA. Lisa, I'm thinking of the message that your talk would have for certain politicians. And what bothers me is that it's very much focused on type 1 errors and avoiding making type 1 errors. And I was a reviewer on the overview chapter of IPCC 3, and the biggest problem was dealing with the insistence that we only deal with type 1 errors. And in fact, the consequences of making type 2 errors, and this is following on Mike's point, are huge. And yet, because it's rubbery, you assume that it's not true, and of course that's completely wrong. How do you and how does IPCC intend to address this real problem of making type 2 errors?
And just before Lisa answers, Brian, could you please say for us what a type 1 and type 2 error are?
A type 1 error is saying something is true when in fact it isn't. And a type 2 error is saying or assuming something is not true when in fact it is.
Thank you.
And it's the distinction in the statistics of using it.
Yeah, it is a very good point. I mean, I guess the point of the talk this evening was to give an idea of the research that I've personally been doing. And in that sense, I've been more looking at what you might call the type 1 errors. But you are right that we definitely in the future have to start working together more to address all type, not just errors, but basically how we interact amongst different communities. Because at the moment, the conversations between the working group 1 type folks with the working group 2 is still a hard conversation to have. And working group 3, I don't think many in working group 1 even have much to do with working group 3. And I mean, Mike might be better to comment on this than me, but there's a definite problem, yes, and I think steps are in place to try and address it, and the way we can do that is basically to just keep having conversations.
My comment would be that it shows.
Yeah.
We'll take 2 more questions, one here, one over here. Jenny, thank you. But here first.
Ian Elson from CSIRO. Sorry, now ANU. My past. If you're thinking about extreme events, the shape of the distribution matters. The shape of the distribution matters as much as the mean.
Yep.
I guess I got the impression from your talk you're talking mainly about means. Can the science tell us anything about what might happen with the shape of the distributions?
Yeah, so one of the slides I showed the global temperature distribution. And in fact, most of the evidence points towards changes in extremes that are predominantly related to changes in the mean. And there's not much evidence that there's a change in variability, for example, for temperature, we're talking about here. But there is a slight, shall we say, a tendency to show a change in skewness of the distribution. So it's skewing towards the hotter part of the distribution. But as I say, this is really, I mean, the distribution that I showed is really the first time that anyone's actually looked at the distribution of daily temperatures. So a lot more work would have to be done on that, and why there is an indication that there might be a change in skewness, I think that we would have a lot more work to look at to see that.
And last question, thank you, Jenny.
How do the models accommodate the likelihood of tipping points, for instance, sudden release of methane from the Arctic?
Well, they don't specifically incorporate events. They just go with the physics of what's actually happening in the model. And if that were to go to a tipping point, then that would be in the model. But it's not constrained on having tipping points or not having tipping points. It really just is about the development of the physics and how that develops over time. And Mike, you might be a better person to talk to about me than that.
Well, I'd like to draw the formal part of the proceedings to a close. And in doing that, I think we would all agree that we've heard a fascinating talk about an absolutely critical issue. And one of the reasons it's critical is the one that Brian Walker's question alluded to. This is one of the absolute fulcrum issues that we face in climate change. It is one of the issues through which the major impacts of climate change are felt, and also through which the major public perceptions of climate change are experienced. People react to climate change through extreme events. And this means that there's a feedback which is amplified by extreme events between what the humans are doing and what the climate system is doing. Each is influencing the other, and that influence occurs to a large degree through extreme events. So I'd like you to join with me in thanking Lisa for a very clear-eyed and careful walk through the science that underpins this really difficult issue. Thank you. Just to conclude, I believe I owe it to the Academy to provide some information about the forthcoming events in this series. The next event in this series, Science Stars of Tomorrow, will be a discussion by Professor Vipul Bansal about organic semiconductors, a topic just as important as the one we've been talking about today, but utterly different. And I am aware that there's another talk coming up in Science Week. Goodness me, who's giving that? It's about the past, present and future of Australian environmental science to be held on the 19th of August here. So thank you very much once again for your attendance and your participation, and welcome back next time. Thank you.